Right, let's talk about radians. Radians are another way that we can measure angles. So we've already looked at degrees. Degrees we're all a little bit more comfortable with. They're a little bit uh, more ingrained in us throughout society and just throughout life. But radians are very important as well. So let's start by defining a radian. One radian is an angular measure which gives an arc length equal in length to the radius of a circle. And so if we think about taking a circle with a radius of r, and bisecting it at some amount, this here would be our arc length. If we were to find that length right there, that would be equal in length to the r. So I don't think I've drawn that perfectly correctly, but that gives us the idea. The arc length, the amount of distance around the outside of the circle, or a portion of the circumference, and we're comparing it to the radius. So the reason that these are important, if we think about degree measure, 360 is kind of random. Why would we choose to break a circle up into 360 degrees? That has no real bearing on the radius of the circle, nor on this arc length that we've just drawn. So the radius and arc length not tied really in any direct fashion with the degree measurement. So where those came from, those were actually kind of ancient math when people were starting to study the sun and its rotation, or the Earth's rotation around the sun, and what they realized is uh, it seems like we're getting back to kind of the same position. The sun gets back to the same position every 360 days, and that was the ballpark for what they thought a year was at the time, 360. And so they chose to break a circle or a rotation up into 360 pieces, and that's where the degrees comes from. But the radians give us another good way to measure an angle, but it ties it to direct elements on that circle, the radius and the arc of that circle. Now, we won't always deal with angles of exactly 1 radian. So how do we find a radian measurement? Well, let me call it theta. Theta is equal to the arc length over the radius. And so we abbreviate these with the letter S and the letter R. R we've seen before, I'm sure. Arc length, we call that the letter S. So we can write that a little bit more concisely. Theta is equal to S over R. So we want to, let me start by tying these to degrees. And I don't want to have to think about degrees every time I think about radians. So we want to move beyond that. But let me think about tying this to degrees first. There is one radian measurement we know already. If we think about a full circle, and we'll call the circle, call it a circle of radius r. We know this arc length. The arc length, because it is the full distance around the circle, we could call that circumference. If we think about the full distance around the circle, that is the circumference of the circle. And so if we wanted to find that circumference, I know that circumference is equal to, we can call it either pi d, or we could write that as pi r to 2 pi r. And so if we take the arc length, we just said that the angle is the arc length. I'm going to use the 2 pi r version of that. I'm going to divide it by r, and that gives me an angle of 2 pi. So that tells me the full rotation of a circle in radian measurements is equal to 2 pi. We said before in degrees that is 360 degrees. So 2 pi has to be equal to 360 degrees. That gives me my first tie-in to my old degree measurements. Notice anytime we have radians, we do not put a unit on that. You can write radians if you want to, but if you ever see an angle without any expression of degree or any expression of what it is, that is always a radian measurement. If you want to write radians or rads, that's fine, but if you leave it off, it's understood to be radians, which is why it's so important that when we're working with degrees, we've got to write that degree symbol there. If we leave the degree symbol off, that indicates that we actually have a radian measure. So if I want to start comparing some things, I could take half of this. That tells me that pi is equal to 180 degrees. If I were to take half of pi, that would be pi over 2. That would be 90 degrees. Obviously, 0 of anything is 0. 0 radians is equal to 0 degrees. To fill in the one that we used to break up our x and y axes before, we had 270 degrees. And 270 degrees, that would have to be the same as 3 pi over 2. We could get that by adding pi over 2 to the pi. 3 pi over 2. So these give me all the axis locations so that we can start breaking up our circle again. So we have 0, we have pi over 2, we have pi, and we have 3 pi over 2 until we get back around to 2 pi, meaning that 2 pi and 0 are coterminal angles. Again, we run into that definition of a coterminal angle giving us the same terminal side. At coterminal angles, we said before, we have to add, subtract 360 degrees. Coterminal angles, when working with radians, we add, subtract 2 pi because 2 pi is a full rotation. So let's work with our radian measures. Let's find some radian angles, or their positions rather, given what we now know about these basic positions. I don't want to have to convert these, I just want to determine where they are. So let's start easy. Let's start with something like pi over 4. Well, pi over 4, if I think about my known positions, pi over 4 is bigger than 0, obviously, but it's not as big as pi over 2. So an easy way to kind of compare this, think about it without the pi. This is just saying we have 1/2 of something. We have 1/2 of pi in this case, and then we're comparing it to 1/4 of pi. 1/4 obviously less than 1/2, and in fact it's exactly half of 1/2. So pi over 4 would have to be here. That would be our terminal side for an angle of pi over 4. We're sketching the terminal side, terminal position. That would be our terminal position. Let's take 5 pi over 3. This one's a little bit more tricky just because the fractions are getting a little bit weirder. We're going to have to be comfortable dealing with fractions here, so we definitely want to practice up on those. But 5 over 3, if we think about that, that is definitely greater than 1. 3 over 3 would be 1. And 5 over 3 is less than 2 because 2 would be equal to 6 pi over 3. Remember, we can always get, if we're comparing things, if we want to know what this comparison is, I would need a common denominator, so I need it to be over 3. Well, we want to multiply the denominator by 3. That means we need to multiply the numerator by 3 as well, and so that would give us 6 pi over 3. And so obviously that's a little bit bigger. If we want to compare it to the pi over 2, that's when we're going to need a different denominator. If I want to compare it to the 3 pi over 2, I can see that my common denominator would be 6, so I'd have to multiply this by 2, and multiply this by 2 as well, this by 3, this by 3, and so I'd have 10 pi, and I'd have 9 pi, obviously this one a little bit bigger. So that 5 pi over 3 is going to be in the 4th quadrant. So just kind of recap what I did there. A lot of times what I'm comparing to first is the pi and the 2 pi, because that's going to show me, am I in the top or am I in the bottom? 5 over 3 definitely greater than 1, so I'm beyond the negative x-axis, but it's less than the 2 pi, so that tells me I'm somewhere in this bottom region. So then I have to compare it to this point right here, which is the 3 pi over 2. I got a common denominator. I found out I'm just past that. It's going to be a little bit closer to the y-axis. It's going to be approximately in there. It's 1/3 of the way along. Only 1/6 off, or pi over 6 over, so it's a third of the way. We can also travel in negative direction. So if we take an angle of, say, negative 7 pi over 4, I'd travel in that backwards direction the same way I did for angles. Well, 7 over 4, I'm going to start by comparing it to a whole pi. So this would be pi in the negative direction. 7 over 4 is greater than that, but 7 over 4 is not as large as 2 pi. So I know I'm either in the the second or first quadrant here, traveling backwards 3 or 4 quadrants. 7 over 4, if I compare it to the 3 pi over 2, well, 3 pi over 2 would be 6 pi over 4, so we can see we're a little bit further than that even. And then 7 over 4 would be halfway from 6 to 8, so that tells me it's going to be in the dead center of these 2 quadrants. That would be my coterminal position. So we want to compare it to those 4 basic positions the same way we did with degrees. We just have to now work with common denominators. We have to think about what our common denominator would be. It is important to know how to work with angles, not only in degree format, but in radian format. Notice on these, I never made a conversion over to degrees. I worked with it solely in terms of radians. We want to be able to do that. I am going to show you how to convert from degrees to radians because that is an important skill too. Let me find my comparisons. Here we go. There are times that we have to work with degrees, or there are times that we have to work with radians, or if we're given a mixed bag, we need to get, of course, all of one or all the other so we can work with the problem, I can work with any of these comparisons, but the easiest one that I see is this comparison right here. Pi equals 180. It's the most simplified, and it's not dealing with any sort of fraction. So pi radians is the same as 180 degrees, which means that this ratio right here, that is equal to 1. If I have anything over itself, that is equal to 1. Even though they don't look the same, they are the same. They are equal to each other. And conversely, if I have 180 over pi, that is also equal to 1. So when I go to convert from one to the other, it doesn't matter which direction I'm going, I'm going to use one of these two. So there is a hard, fast rule that the book gives us for which one we need to multiply by. I'm not going to write that up here yet. I'm going to have us think about it. So let's start let's take the 5 pi over 3 we dealt with just a few minutes ago. I want to convert this to degrees. Well, if I look at 5 pi over 3, we're going to have to multiply by either this or that. Right now, we know this is radians. Remember, we didn't write there, but we know it is a radian, and our goal is to get to degrees. And so, if we look at our units, we want degrees, we want the radians to cancel. So which of these two ratios should I be using in order to do a unit conversion? I'm going to multiply by one of these two things. If radians are on top, I want radians on the bottom to cancel, and that will leave the degrees to survive. I'm going to multiply it by the 180 over pi. Because then our radians cancels. If we look at what else simplifies, the pi's happen to simplify. Don't just think because you see a pi that guarantees the pi's are going to go on the bottom. Pi's can be in degrees, but in this case, the pi's do cancel. We also see that 3 goes into 180 60 times. So we're left with 5 times 60, which is 300 degrees. So to write that a little bit clearer, 300, and then our degree symbol would get stuck on top right there, 300 degrees. Let's go the other direction. Let's take 15 pi degrees. So I've tried to trick you. I've stuck that pi in there. Even though it's a degree measure, I've stuck the pi there. Pi's can be in degrees. It doesn't mean that it's a radian. And I want to convert this time to radians. That's my goal. So if I want to convert to radians, I again can multiply either by the pi over 180 or the 180 over pi. Well, this time because I'm starting with degrees, if I'm going to multiply, I need those degrees to be on the bottom. So I'm going to multiply by the pi over the 180. I can see that the degrees cancel. I can do a little more simplification here. I know that 15 goes into 180. And so we can use our calculators. We could do it a little bit at a time. 180 divided by 15 is going to give me 12. And so I'm going to be left with 12 on the bottom. But I can see now the pi's don't cancel. I'm going to end up with pi squared on top, and now I'm going to end up with the 12 on the bottom. And if I want to leave it in exact form, that's fine. I don't have to have a nice, pretty 5 pi every single time. We've ended up where those pi's are still there, and in fact, they've become pi squared. So very easy to convert from degrees to radians.